Welcome to session 17, part 2, as we continue our discussion on plane stress. In this part of the video, or in this part of the session, we're going to discuss a set of generalized equations that describe these 2D transformed elements. In other words, that tedious performance of equilibrium on an element is not something that we typically do. We would first go to kind of a generalized set of equations that we can utilize, or use stress tensors and rotations, or eventually we will use more circle, okay, to be able to do and visualize these transformations for 2D elements. Okay, so this portion essentially says or starts off with defining sigma x, sigma y on a planar element and saying, okay, we know that these are going to be, we're going to think in terms of positive x, y, and theta as a rotation, which we can see here, okay, like this, to go from this state of sigma x, sigma y, or this depicted state with sigma x, sigma y, tau xy, to sigma x prime, sigma y prime, tau x prime, y prime. And, before we were kind of plugging numbers in and then, doing the slices and keeping track of everything. Now we're going to essentially just keep things in terms of variables and do the slicing and dicing. Okay. For example, here, okay, which this cut is the same as rotating the element positively, as you see here, right? Just putting this out there, okay? Same angle theta. Again, easier to see if we use exaggerated cuts, meaning that, okay, we want to say that, okay, don't go over 45 degrees with this theta. And instead of plugging numbers in, we're going to essentially just use the variables and the angles and be able to write up a generalized equation, okay? And if you want, you can take a look at Hibbeler's book or others for this derivation, okay? And we'll go through it rather quickly, okay? But this is equilibrium solving for sigma x prime, all right, delta A, all right? And we have remember we said we had 5 components essentially that we need to keep track of. And here they are with 2 stresses, 2 shear stresses represented and 2 normal stresses represented. And this can simplify to this equation, which can then be moved. This is the same equation, just moved up, viewed with a few more trigonometric identities to get this equation. Okay, so sigma x prime is equal to the mean, all right, of the 2 normal stresses plus the difference divided by 2 of the normal stresses, and times cosine 2 theta plus tau xy times sine 2 theta. Now this is something that you probably want to write down on your formula sheet, but I hope you don't use it. Okay, to be honest, you're going to use it for the homework, all right? But by the time we get to the exam, actually, I hope I'll have to see when I have to look. But by the time we get to the exam, I think we will have covered more circle, and so that will be the more elegant and faster way to do things. But this equation always works, okay? And there are probably many of us who just use this equation for sigma x prime, all right? Similarly, we can perform equilibrium on in the y prime direction, okay? So this was in the x prime direction previously, but now in the y prime direction. And we have the 5 components, and we get tau x prime y prime equal to this. Move it up here, find a few more trigonometric identities, and voila, this is what tau x prime y prime looks like. Okay. And then kind of a nice little trick is to say, oh, we want sigma y prime as well. Well, guess what? If I just rotate, okay, my sigma x prime 90 degrees, I get to sigma y prime. Okay, and so we can take our equation that we have for sigma x prime, add 90 degrees, and then figure out what sigma y prime is, and that's what we have here. Okay, so these three equations, definitely put them on a sheet, but I don't remember them. Okay, I don't have them memorized, but put them down on a sheet. They're good to have around, and then in a little bit, in a couple more sessions, we'll have a nice what most mechanical engineers think is a nicer way to do these 2D transformations. Now, here's an example. It's actually remarkably familiar. Okay, so sigma x equals 50 megapascals, sigma y equals 100 megapascals, and tau xy equals 0. Okay, and what are sigma x prime, sigma y prime, and tau x prime, y prime? Okay, when we have 30-degree angle of rotation. So we can go ahead and use this equation for sigma x prime. Okay, plug it in to Python if you like. All right, so you can look at the Colab, which is associated with this assignment, and we can go from here. All right. So this is a pretty straightforward way to calculate out sigma x prime, tau x y prime, or tau x prime y prime, and sigma y prime. Okay. Now, we can also use this equation to come up with a little bit more of an intuition of what's happening, all right, as we rotate. So here we're saying we have the sigma x equals 50 megapascals. The sigma y is equal to 100 megapascals. Sorry, that got chopped off. Okay, and tau xy is equal to 75 megapascals. All right, so I'll just I don't know, this is just so you can see a little bit better. This is 100 megapascals. Okay. And what's going on if the angle of rotation, all right, varies from 0 to 180 degrees? Well, now that we have these transformation equations, we can plot that evolution, okay? We can see that sigma x prime, it rises, all right, up to a maximum, and it comes down to a minimum, all right? And we can also see that the tau x prime goes through 0, all right? And then it goes even lower. We can see, and actually this is symmetric, all right, which is not lost on us, or won't be later, okay? But this is symmetric, whereas sigma x prime and sigma y prime are not necessarily symmetric, okay? And you can kind of get this this perspective that this kind of has twice the frequency. All right, you see these? I mean, these are in terms of rotation angles, right? This is not against time, but you kind of have twice as many, right? You have kind of well, am I actually, wait, no, I'm wrong. We have one trough. They're just out of phase with each other. Okay, let's leave it at that. Sorry, I apologize. Okay. So the question here, all right, is if you have a state of stress, and I would like you to use these relationships to estimate the angle of rotation, okay, required to have tau x prime y prime equal to 0, okay, and then submit the value closest to 0 degrees. All right, as theta plus or minus 90 degrees actually is also a solution, but just pick one that's closest to 0 degrees. Okay, yeah, that concludes this portion. Much shorter than the last one. See you in the next one.